I have very exciting news to share for this episode. As I was preparing it, it became clear that my universe's expansion itself makes room for many classes of waves to arise, some short-lived, some that exhibit wave-like behavior and later on become massive, with no wave oscillations and so on. The key takeaway I want to leave you with is the fact that my universe accounts for the genesis of particles. Let my universe's scientists figure out how those indigenous particles decay into the particles that they live within. That problem is too hard for me to deal with. Let me break down the search process for you. We start from the results of episode 6, where we established that the energy and momentum that can arise from the universe itself are complex. Then, we allow for there to be an affine relation between the actual wave energies and momenta and the modes that we discovered in the earlier episode. This allows us to explore a space of waves where the modes that show enough regularity can give rise to elements that we can select as ways that manifest into my universe's particles. Since the energy and momentum are complex, to derive the mass of the hypothetical particles that match the said energy and momentum, I suggest we use the modulus squared in the Klein-Gordon formula. Modulus squared of energy minus modulus squared of momentum equals modulus squared of mass. In my universe, I can try different affine combinations for the energy and momentum to look for regular patterns that would suggest some viable massive or massless particles. I particularly need these kinds of particles to start showing oscillation after time t equals 0, so as to be appropriate candidates to appear in a universe that has a finite age, or a clear beginning. As you tune the parameters and try different combinations, a peculiar class of particles can appear, that actually have an oscillating energy pattern forever, starting at t equals 0, and even seem to exhibit massive properties, provided they have an ever-constant null momentum. They would obviously not be able to maintain that ever-null momentum as the curvature of spacetime requires, due to gravity. So, I am just guessing that their appearance would be short-lived and they would have to decay into entangled pairs of appropriate momentum, as soon as gravity prompts them to move. These particles would tend to cause spacetime curvature as time passes from origin, and they would soon extract multiple pairs out of their siblings, as those would start acquiring high enough speeds. My reasoning is that, slowly moving such massive particles can retain their nature, because the movement would not induce too much oscillations. However, those who tend to acquire oscillations because of the curvature of spacetime will end up decaying into other particles that we have yet to find a model for. Now, I have no justification for why I would need to combine my earlier obtained functions of energy and momentum in an affine way, but this specific combination seems to exhibit good features that I might find good arguments for, since this is an imaginary universe. After the redirect, I will discuss the implications imposed by an imaginary scaling factor between t equals minus lambda and t equals 0. But let me leave you with this result stemming from work presented in episode 6. I noticed that if you reflect the curve for energy and offset it by a half-life, the model for energy and momentum are equal in modulus up to a multiplicative constant. Given the offset, and the requirement of such a transformation, this seems to suggest that what we have so far called the half-life of the universe is some form of displacement between the origin of the time coordinate and the origin of the radial coordinate. This means that, the reason there's anything to begin with is because, for some reason, you would have to have been here and then, simultaneously, or perhaps there and now. The half-life parameter seems to capture that stress between the coordinates of space and time, which wouldn't agree to be null at the same time. This means that what we called time t equals 0 when the scaling factor was null, is rather time t equals the half-life. Or, to put it otherwise, the universe was already one half-life old when it got to acquire a space grid. This echoes the idea that between these two milestones, things took place that suggest whatever was there was traveling beyond the speed of light as the grid was collapsing into itself from a prior universe. This is what I would hope to deliver after the redirect.